Thank you. So, good morning, everybody. Thank you very much for the introduction, and thanks for the invitation. I really do appreciate it. I'm glad to be here. Thank you very much, guys. And thanks to all of you for coming back after coffee break to listen to my talk on the last day. I would like to start by recalling the basic concepts of the entire workshop. What I'm going to show you today is something along very different lines from what we have heard up to now in the workshop. Nevertheless, the experiment was performed on a material that is classified as an altermagnet. And I'm definitely going to discuss emergent opportunities and novel frontiers. Let me now mention a couple of keywords that fully define our approach to magnetic phenomena. We do operate on fundamental timescales. These are timescales, intrinsic and characteristic timescales of collective excitations of the lattice, of spins, and electrons in solids. And they turn out to be in the picosecond and femtosecond regime. We focus almost exclusively on coherent effects, because coherence allows us to manipulate the macroscopic magnetic order in solids with extremely limited, virtually with no energy dissipations. In this framework, we try to establish some phenomena that typically are labeled under the name nonlinear magnonics, but that's a very general term, so it means everything and nothing. I want to be way more specific than that, and I would like to state that we try to establish the modification of the spectrum of collective magnetic excitations, and even to couple different magnon modes, always in this framework. So, fundamental timescales, coherent effects. Now, these keywords do not simply define what we do, but they also steer our selection of materials. We have to work with materials with a band gap. Band gap means no free electrons, no Joule heating, so we can access coherent effects. And mostly we work with antiferromagnets. I don't think I need to define antiferromagnets for this audience, and I don't think I need to convince you that it makes sense, it's a good idea to work with antiferromagnets. What I would like to say is that in view of the keywords that I gave you, I'm definitely not going to discuss methods to characterize the ground state. I am interested in excitations. Collective excitations, magnons, spin wave. The entire set of collective excitation for a single magnetic material is given by the dispersion relation of magnons. Now, the dispersion relation is a sort of DNA, of magnetic DNA of the material, because it describes a unique set of possible excitations of that given magnetic material. I know that sounds like very basic knowledge, but this will come back in a couple of slides. Now, we operate on fundamental timescales, so we have to use femtosecond laser pulses to excite and probe spin dynamics. And if you look at the wave vector scale of the whole Brillouin zone, the wave vector of light is 0. So most likely, optically, you're going to work at the center of the Brillouin zone. There are several ways to excite coherent magnons at the center of the Brillouin zone on fundamental timescales. You can classify all the mechanisms as either resonant or non-resonant. The most easy thing, a straightforward thing that you can do in the resonant case is using laser pulses, the magnetic field of which oscillates at the same frequency of the magnons. And then you can induce a picosecond version of the Zeeman torque, generating a macroscopic spin precession. Or you can use the laser pulses to induce strain waves in magnetoelastic materials. Then the strain wave, in turn, will couple to spins generating spin waves. Or you can use electronic transition. Electronic transition coupled to magnetism. I'm referring to the so-called exciton magnon. That's an electronic transition, an exciton with spin flip, delta S1, that takes place simultaneously with the generation of a magnon, so that overall the spin conservation is restored. If you pump the transition, you do resonantly excite magnons. In some cases so efficiently that you can even drive a magnetic phase transition in 600 femtoseconds. Or if you want to do something a bit more elegant, you can take one of the most famous antiferromagnets, nickel oxide, in its pristine form, multi-domain state, like it is found in nature, and you can, with the exciton magnon, pump coherent terahertz magnons in one domain that basically couple to gigahertz coherent magnons in other domains via an interaction taking place at the walls. So spins in the walls are mediating the coupling. Fine, these are all examples of resonant pumping. There are non-resonant excitations or non-resonant mechanisms to induce spin waves, and we have briefly already seen this. Alexei discussed this in the time domain. The excitation mechanism here is light scattering of magnon. This is called impulsive stimulated Raman scattering, so ISRS from now on. Light scattering of magnons is a very general concept. It is non-resonant, so you don't need to match the frequency of the magnons with your light beam. Since it is a really general concept, you do not require any exotic properties from your material. It is not surprising that it has been demonstrated for a lot of material classes in the center of the Brillouin zone. To be honest, you can even push ISRS to work in different parts or regions of the dispersion. You can use it to generate magnons near the edges of the Brillouin zone. If you wonder how comes that light with zero wave vector can couple to such high wave vector magnons, you can imagine the process in the following way. You take your antiferromagnet in the ground state and you flip one spin per sublattice. If you do that, both sublattices are going to be reduced, but they are still equivalent. You haven't broken the balance of the two sublattices, which means that the total spin of the system is still zero. So this excitation is a delta S equals 0 process. But when you flip spins in a magnetic material, you trigger magnons. That's unavoidable. And you have triggered two of them. If they have the same and opposite wave vector, k minus k, you can also conserve the wave vector. And that's something that you need for an optical excitation. Delta S 0, delta K 0 are the conservation laws for optical excitations. And again, I'm talking about light scattering. We did demonstrate this years ago using green laser pulses, photon energy 2.2 electron volt. And we managed to pump coherent magnons with energy of 88 millielectron volt, so non-resonant. That means in frequency 22 terahertz. The signal was fully coherent, we could fully manipulate it. As you see from the publication date, that's rather old stuff. I'm not talking about this today, I'm mentioning this because still nowadays, this particular regime of spin dynamics has been barely investigated. There are a lot of good questions that are not answered yet. In particular, in terms of spin dynamics, not much about excitation mechanism, which is still not trivial. In the original paper, 2016, we put forward a theory for dynamics of the spin correlation function. Later on, we started to work together with Johan Mentig and Ellen Gomonai. They did develop a quantum mechanical model that can describe the spin dynamics, and the prediction of the model is that these pairs of magnons are even quantum mechanically entangled. A lot of things can be done here, and I hope will be done here. Not talking about this today. What I wanted to tell you with this very brief, highly incomplete and strongly biased introduction is that there are several ways to kick magnons on fundamental timescales in the electric material, so in a coherent way. Resonant and non-resonant mechanisms. They both work like a beauty in the center of the Brillouin zone. ISRS can be pushed even to the zone edges. What is missing in the literature is a resonant pumping of zone edge magnons. Now, to start to address this point, I would like to introduce a material that we have already discussed in the week, hematite. I just remind you that we only discussed today 300 Kelvin experiments, so that's in a pictorial way the ground state. We don't operate below the Morin phase transition, only room temperature today. Roughly 20 years ago, some colleagues from Japan published the absorption spectrum of hematite in mid-infrared spectral range. And they did observe this peak that they call 2SW. That corresponds to the 2 magnon mode. The frequency is 45 terahertz, and it corresponds to the frequency of a magnon pair near the edges of the Brillouin zone. The experiment was done in a very systematic way. The data were interpreted in terms of group theory, so it's a really good experimental paper. Among all the things that the authors concluded, the most important for us is that this absorption peak in nature is an electric dipole transition. So the electric field of light being absorbed generates these magnon pairs near the zone edges. If you wonder, okay, how comes that happens? There is an excitation mechanism explaining this, which is called exchange mechanism, and is not introduced here, is a much older story, it dates back to '65. The basic idea is taking two nearest neighbor atoms in an antiferromagnet, which means atoms belonging to different sublattices. If you do consider just the ground state and one excited state split by the exchange interaction, you can identify electric dipole transition that results in flipping to spins, provided that the electric field of light is resonant with the frequency of the 2 magnon mode. You don't need to consider any other interaction at the lowest order to describe this effect. Good. The experiment was performed on a single crystal, bulk. We took a single crystal bulk, we reproduced the literature in a qualitatively and quantitative way. Now, the 2 magnon mode is a very weird magnetic excitation. It's different from any other possible magnetic excitation that you can imagine. And to explain what I do mean by this, let me show you the dispersion relation of magnons measured by means of neutron spectroscopy long time ago. I'm using this plot, very old, because I need the energy axis. I told you that you can do beautiful physics using laser pulses in the center of the Brillouin zone. If you don't care about ultrafast, about control, about coherence, you only care about magnons, you don't need anything of what I told you so far. What you do is simply, you take your crystal, you set the temperature to the proper value, and you populate your magnonic level. That's it, thermopopulation, adiabatic process, and you can use thermodynamics to describe it. And you can go further with this process. You can keep increasing the temperature, and you can populate all the magnonic states. Fine. It works within a certain extent. If you try now with temperature adiabatically to populate zone-edge magnons, you find out that that's impossible. Before you succeed this, you have pushed your system into the paramagnetic phase. Clearly, if you work close to the nil temperature, you can calculate your Maxwell-Boltzmann distribution, if you are more fancy than me, Bose-Einstein, and you are going to have a tail of the statistic distribution covering the edges. Exponential function doesn't go to 0. But that's not a massive population. It's a minor effect. If you want to massively populate magnons near the zone edges, you have to use light, or formulate it in another way. That process doesn't exist in a thermodynamic world. Now, we have this very peculiar magnetic state, and we know from the papers of our Japanese colleagues that in hematite, with light, you can really populate these states. In this situation, I believe that a fundamental question is really looming over the horizon. Now, you don't take a lamp. You take femtosecond laser pulses, super strong, and you can massively populate in an impulsive way this excited state. Which kind of spin dynamics are we going to induce and observe? Or formulate it in a different way. If you do that, what the hell is going to happen to the magnetic system? Truth to be told, I'm not the first guy thinking that that might be interesting. Very recently, 50 years ago, theories, again from Japan, published 2 papers predicting the following effect. If you can populate strongly enough zone-edge magnons, you are going to activate magnon modes throughout the dispersion, not the one that you pump. And these newly activated magnons are going to have a different spectrum than what you can infer for the dispersion. Because the main consequence of pumping strongly at the zone edges is a modification of the entire dispersion relation. That was the prediction, and they call this effect instability of the magnetic structure. Very bold statement put forward 50 years ago. Now, the experiments that we perform has a very canonical layout. We have a laser beam to pump magnons and another laser beam to probe spin dynamics via magneto-optics. What is not canonical by any stretch of the imagination now is the laser technology. Because now we have to operate in mid-infrared spectral range, and we need very strong laser pulses, and we must be able to change all of the properties of the pulses. Photon energy, pumping resonantly and off resonantly. Duration, polarization, everything. That's one of the main reasons why 2.5 years ago I moved to Konstanz. Because I had the chance to be hosted by Professor Alfred Leitenstorfer, who, among many other things, has developed a laser source operating in the mid-infrared spectral range, matching all of these requirements. And I think it's safe to state, outperforming commercialized sources. It's completely homemade system. To show you what the laser can do, let me show you what the electric field looks like when we tune the source to be resonant with 45 terahertz. The oscillation of the electric field are in the regime of 8 megavolt per centimeter, which is considered strong field, intense field. That's attenuated by factor 100. So this laser is seriously a beast. And if you wonder, okay, how does the spectrum compare to the transition? The line widths are comparable, and we can tune it, so we can pump resonantly and off resonantly. And honestly, the very first experiment was performed pumping very far away from the 2 magnon mode. And we observed the spin dynamics. These are the experimental conditions, so we can see an oscillatory pattern with 2 frequencies inside, which amounts to 165 and 20 gigahertz. These numbers match very well the resonances of all the frequencies of the 2 resonances in hematite, quasi-antiferromagnetic and quasi-ferromagnetic mode. So K0 magnons. Now we want to be even more sure that these oscillations do really correspond to these modes, So we perform measurements as a function of the magnetic field that we can apply. We can apply a very weak field. In this weak field regime, the frequency of the antiferromagnetic mode doesn't change, as expected, while the frequency of the ferromagnetic mode scales with the field. We feed the data with the standard equation describing the ferromagnetic frequency in weak ferromagnets, and from the fit, the white line, we obtain gamma. Our value of gamma is consistent with the literature, and the literature access this 20 gigahertz mode with a completely different setup with electrical methods. So we can confidently conclude that the oscillations do correspond to the two resonance modes. Now, I show you this. Evidently, we want to do this. And before showing you all the systematic measurement that we did, I would like just to give you a flavor of what we're talking about, to compare the off-resonance case which we've just discussed with what happens when we pump on top of the resonance, perturbing as much as we can the magnetic system. In that case, that's what happens. Two modes are still there to be seen, but the signal is dramatically and wildly different. Clearly, we did our work, I believe, properly, in the sense that we changed with small steps the pump photon energy, and for each time trace, which corresponds to a different value of the pump frequency, we can now take the oscillation profile, feed the data, and get amplitude and frequency of our magnetic resonances. And you can build plots like this one, showing that the amplitude of the antiferromagnetic mode is increased by a factor 5 when we pump the 2 magnum mode, and showing that the ferromagnetic mode has a very similar behavior, although the amplification is slightly less pronounced. Now, let me get this straight. What you're not looking at here right now is the following. I'm not telling you I have a magnetic transition, I pump resonance, I have big oscillations, I go far away, oscillations fade. No. I'm telling you that we pump 45 terahertz magnons at the zone edges. And for some reason, magnons in K0 with frequencies that have nothing to do with 45 terahertz gets amplified. That's what you're looking at. And that's just the story for the amplitude. What about the frequency? The frequency of the antiferromagnetic mode increases when we pump resonantly, while the ferromagnetic mode softens. And that's something that we got just looking at the data. No modeling, no theory, no simplification, no nothing. So looking at the data, we get that the spectrum of the photoinduced magnons is modified, which means that the dispersion relation is modified. Now, how can we formulate this? We did take hematite, we did pump the 2 magnum mode, and changing the dispersion in the transient state, we did transform hematite into different magnetic material. And please, take a look on how the frequencies have changed. The higher mode, higher frequency mode, blue shifts, while the lower frequency mode, red shifts. That's the typical change in frequencies that you observe if the two modes are coupled, two general modes. In addition, for the specific case of hematite, you can induce exactly that frequency shift, as demonstrated in the literature, if you apply a very strong field, stronger than 5 Tesla, into a different experimental geometry than ours. So, we observe fingerprints, at least, of coupling between the two modes, and what we do to the frequencies is equivalent to apply a monster field of more than 5 Tesla. Now, in our experiments, we do observe signal when we pump resonantly, very strong, but we also observe no zero signal when we are outside of the resonance. To me, this scenario triggers a first question. Are these two regimes two separate stories, or are we looking at a single mechanism that we activate either resonantly or off-resonantly? We did address this question purely experimentally. I'm not showing you any further data, unless somebody's going to ask, clearly. But experimentally, we can answer this, showing that there is only one mechanism that we can activate either resonantly or not resonantly, and this mechanism is non-thermal. Please let me be precise. With the word thermal, I mean anything that scales with the amount of energy deposited by the pump pulses in the material. That can be demonstrated experimentally. And to be 200% honest, everything that we see pumping off resonantly is fully consistent with the original picture of impulsive stimulated Raman scattering in magnons provided in 2005 in the paper by Alexei. But then we have to deal with the resonance. So how do we describe it? I think it's natural to extend the impulsive stimulated Raman scattering into a resonant picture. And again, to be complete, Resonant ISRS on phonons is textbook. Resonant ISRS on magnons, there is one paper out, highly debated, but what is completely unheard of is that the resonance of the Raman cross-section for K0 magnons originates from high-energy magnons. That's something that for sure we didn't have in our minds until we measured this. So it's not an easy task or an easy job to write down a proper theory for this, and we're collaborating with Dominic Urasha for that, University of Tel Aviv in Israel. I would like to touch upon a point as the last point of my talk, which is again about the dispersion relation modification. I'm telling you we change the dispersion relation, fine. The legitimate question is how much? I show you the changing frequency. We may try to convert this changing frequency in modification of the interactions to have an idea of how strong the pumping scheme is. I don't want to claim that I did theory. I did some calculation that an experimentalist can handle. So what I did, I took the equation for the ferromagnetic resonance, knowing that gamma is something that we got numerically from our fitting. H is the magnetic field that we apply. HD is the effective field due to the DMI, known for hematite. We know how much we change the frequency from the experiments, from the data, so we estimate with that derivative that the DMI is softened by almost 10%. And you can do something similar with the other frequency. This time you have to deal with this H²C term, which is the product of exchange and anisotropy. Just knowing how much we change the frequency of the antiferromagnetic mode, we estimate H²C to be changed by 12%. We can't disentangle exchange and anisotropy contribution, but we do expect the exchange to be dominant because the optical excitation is delta S0, which shouldn't trigger, in the first approximation, big dynamics of anisotropy. Now, I'm not going to repeat what I've said, but I want to say that if you're able to pump magnons at the zone edges in a resonant way, you are in for a new physical playground. This is the very first experiment in this direction, and we have already observed highly unexpected, exotic, and phenomenal spin dynamics. Let me conclude thanking my team, Team Falcon at the University of Konstanz, in particular the people involved in the project. So Christoph Schoenfeld, he did all the measurements that you have seen, and Julian Baer, who has recently joined our project. Out of all the collaborators, I would like to explicitly thank Professor Leitenstorfer. He's my host in Konstanz, and the funding agencies, which for me means almost exclusively the DFG, via the M-Minuta program and the SFB 1432. Look forward to your smart questions. Thank you very much for your attention.